completed with this topic, interference. And the last topic that we had seen was intensity distribution curve. Right, this was exactly where we had stopped. So here we had seen that this, because of non-coherent sources and coherent sources, you obtain two types of graph. For coherent sources, you obtain such a type of graph where the maximum intensity is 4i and the minimum intensity is 0. For non-coherent sources in intensity is independent of the phase difference. So it's simply a straight line. The rest of the things for interference, we had seen bright fringe, all these things, interference with white light. We didn't do numericals on this, no? Let's do numerical. See, this numerical says that a beam of light consisting of two wavelengths, 800 nanometer and 600 nanometer. This is used to obtain interference fringe in YDSE, that is Young's double slit experiment, on a screen placed 1.4 meters away. So remember, capital D we had taken. That was the separation between the source and between the slit, double slit, and the screen. So that capital D here, it is given as 1.4 meters. If two slits are separated by 0.28 millimeters, both the slits, they are separated by 0.28 millimeters. So remember, in the formula, small d we had taken. Small d was what? It was the separation between both the slits. So if it is the separation between both the slits, this becomes 0.28 millimeter. This is small d. So if two slits are separated by 0.8 millimeter, calculate the least distance from central bright fringe where the bright fringe of the two wavelengths coincide. Now, what is meant by this? Where both the wavelengths coincide? See, I have told you that at the center, you get a very, very bright fringe, which we call as the central bright fringe. So if any of the fringe that we take it from the distance, just a second. Yes, class. So see this question, remember I had told you that from the central bright fringe you obtain. And if you want to find out the separation of any of the fringe from the central bright fringe, you take the linear separation, y that we had calculated for bright fringe separately, for dark fringe separately. So now this is saying a beam of light is incident having two wavelengths. So 800 nanometer has its fringe widths. I'll show you. This is the figure. So 800 nanometer has its own fringes, and the red color that is showing you the other one, which is 600 nanometer. This is showing you another fringes. So at a particular point where both the fringes will coincide, it's like you have a series of 800 nanometers fringes and you have a series of 600 nanometers fringes. Like this you have it. So at only one specific particular point, you will be obtaining a point where both the wavelengths fringes will coincide. Now, it can happen that a bright and a dark has coincided. It can happen both the darks have coincided. It can happen that both the brights have coincided. So now which condition will we choose? So it has mentioned you in the question that calculate the least distance from the central bright fringe where the bright fringe of the two wavelengths coincide. So let's say for the 800 nanometer, the separation is yn. And for the red one, that is the 600 nanometer, separation is yn. So at the end, what can we conclude? At the end, if this separation is yn, this separation is ym, and both are coinciding, it means both are equal. So formula for the bright fringe, remember for formula for the bright fringe, we had seen y is equal to n lambda capital D by small d. So here this will become n lambda 1 capital D by small d is equal to m lambda 2 capital D by small d. So capital D gets cancelled, small d gets cancelled. And I have chosen as a number of fringe for the red one. Red colors are just depicting that 800 and 600 nanometers. Now see, n into lambda 1 is equal to m into lambda 2. Right. Now, lambda 1 is given as 800 and lambda 2 is given as 600. So, n is what? N is lambda 2 by lambda 1 into m. Put in the values. n is equal to lambda 2 was 600. So 600 nanometer by 800 nanometers into m. So nanometer cancels this nanometer. We will be left with 3 by 4 m. Now, we didn't get any answer. N was the number of fringe for the 800 one. M was the number of fringes for the 600 one. But we didn't get any answer. N is equal to 3 by 4 m. You are getting it. You don't know what is the number. How will you solve this question? How will you get your final answer? What are we doing? We have to find out yn and ym. But the problem that is arising, we don't know n, we don't know m. How will we solve this question? How will we find yn or ym? So that's why we are trying to find out n and m. But when we use this equation, we use this method, again we arrived at the fact that n is equal to 3 by 4m. So it means something still is missing. We want to find out what is the value of n and m. Now C class. Can these fringes be ever in fraction or be ever in decimals? Obviously not. They'll always have a fixed value. All these will be having a fixed number, a fixed value. Like 3 fringes, 4 fringes, 5 fringes, 6 fringes, like this they'll be having. You won't have 3.5 fringes is formed or 0.38 fringe has been formed. Obviously not. It means you cannot have n or m in fractions or decimals. It means n or m has to be a complete whole number for this occurrence. So see, if I choose the value of m as 0, I get n as 0. So m as 0, n as 0, this is only possible for the central bright fringe. This is only possible for the central bright fringe. So it means m cannot be 0 and n cannot be 0 definitely. So next number becomes what? Next number becomes 1. If we put m as 1, we get n as 3 by 4 into 1, that is 3 by 4. So m can be 1, but can n ever be 3 by 4? Can you ever get 0.5 fringes? 0.6, 3 by 4 is actually 0.6 only. So will you ever get some values like the 0.7 fringes? No. 3 by 4 is itself a fraction. It means this value is not possible. So this value is not possible. Moving on to next number. This becomes 3 by 4 into 2. That becomes 3 by 2. Again, fraction you cannot have. M is equal to 3. N is equal to 3 by 4 into 3. That gives 9 by 4. Again, not possible. As soon as you put m as 4, n becomes 3 by 4 into 4. 4 gets cancelled, you get 3. Now see, is it possible that the fourth fringe from the 800 wavelength and the third fringe from the 600 wavelength coincide? Now, why did we choose this? We could have chosen m as 8 as well. Then also we would have got a proper number, right? A whole number we would have got. Why not any other number except for 4? Because your question demands that calculate the least distance from central bright fringe. So if you are calculating the least distance, so you have to choose the minimum value that is possible. So m is equal to 4, n is equal to 3. This is the only solution that is possible. This means what? Fourth bright fringe of lambda 2. Fourth, because m is equal to 4. So fourth bright fringe of lambda 2 will coincide with third bright fringe of lambda 1. This is the meaning of it. Now it basically means what? It is like this is the central bright fringe. This one is the fringe. This one is the first bright from, this is the second, this is the third one. This is from lambda 1. And from lambda 2, from lambda 2, you are getting 1, 2, 3, and 4. So ultimately at this particular point for lambda 2, both are coinciding. So it means separation, this will be the same, and this separation only we are trying to find out. Now you have values of n and m, both of the values you have. So yn is equal to n lambda 1 capital D by small d, you can put, you have all the values with you. Or ym is equal to n lambda 2 capital D by small d. This also you can put. From both of it, you will get the same answer. So anything you can do. It's just that this is a formula based, this end part, this part is a formula based part. But to get n and m, here it will be m. To get n and m, you have to have the values of it. Fine, so this was a question that was needed. And this type of question comes a lot in your exam. And this is very easy. See, when you will reach this step, you will automatically understand that whatever is the denominator, you have to put it. Otherwise, rest of the things that you will be getting will not be the same. So whatever is the denominator, that becomes m. Solve it, you get n. Whenever you have such types of questions. Note down the question, then note down the solution. Any doubts you have in between, let me know. Any part you want me to repeat, let me know. Text me in the chat box or directly unmute yourself or ask me. Keep on noting it. Wherever you get stuck, let me know. See class, this question says what? This says that this figure is given to you. You have to state the condition for constructive interference, destructive interference, obtain the fringe width. You have to locate the position of central fringe. Now see what is the difference. This is just exactly the derivation what we have done. So what is the difference that has arisen here? See class, when we did the derivation, whenever that in the last class we did this derivation, we had this part S1P, we had this part S2P. So S2P minus S1P, this was the path difference that we had obtained and the whole expression was obtained. Now what is happening? Now you have additional waves that are also coming from the source, that is SS1 and SS2. So that's why you just have a change and a difference in your answer, that is lambda by 4 given to you. Look here, SS2 minus SS1 is equal to lambda by 4. From here, look here. So that's why this additional extra part that you're obtaining, this additional extra part, this is just making your answer different. Rest of the things were same. Now see, firstly, let us write the path difference. Now path difference will be what? Instead of just S2P minus S1P, you will have this entire minus this entire term. So it means the path difference that you will obtain, see, it will be what? X will be firstly one side, that is SS2 plus S2P, one side, now minus the other side. Fine. Now see, just solve the brackets, open up the bracket. So this becomes SS2 minus SS1 and this becomes plus S2P minus S1P. Fine, this much you have. Now SS2 minus SS1 is what? This is already given in the question, that is lambda by 4. This part is already provided in the question. And this we had derived in the last class. X, the path difference that came. Y and small d by capital D, remember? So it's just that X was equal to this term. Now you are having this additional term. This is just the difference that has arisen. This additional term you are having. So X, this will become lambda by 4 plus yn small d by capital D. Now let's solve this. So let's bring this here. Minus lambda by 4. This will become equal to now yn small d by capital D. So capital D by small d, x minus lambda by 4. This will become yn. Yn was what? This was only lambda capital D by small d. Now because of this factor, you are getting this also. And in terms of just x was yn small d by capital D. When we solved this, this became x capital D by small d. But now you're not just getting this term, you are getting this entire term. Why? Because you have additional path differences now. That is SS1 minus SS2P. Because of lambda by 4, you're getting it. Now see, now you can start solving it. You now have the equation with you. You have this equation with you. This will help you for constructive interference. First part says constructive interference. For constructive interference class, what is the condition? X equals to n lambda. Remember we had done this condition. So see, put it in the formula instead of x, right? Capital D by small d is there. Instead of x, I'll write n lambda minus lambda by 4 is equal to yn. So yn will be equal to lambda capital D by small d n minus 1 by 4. Even if you have the values, you can put it in the question. Not only constructive, now we had to find for destructive as well. See, destructive interference. X is equal to 2n plus 2n minus 1 lambda by 2. N minus 1 lambda by 2. So instead of x in the formula, put it. So this becomes 2 minus 1 lambda by, okay, 2 was already there in the formula. So that becomes 4 minus lambda by 4. This is equal to yn. So see, yn will be capital D by small d, 2n lambda by 4 minus lambda by 4 minus lambda by 4. This will be it, right? If we expand it, so what we'll get? So yn will be what? Capital D by small d is there. Lambda by 4 can also be taken common. We are left with 2n minus 2. Just check the calculations when you're writing. If there is any error, let me know. Second part said fringe width. Now, same thing we'll do the way we had done the derivation of fringe width. How did we calculate the fringe width? Remember, we calculated it like yn minus 1. Same thing we'll do it here. This becomes lambda capital D by small d n minus 1 by 4 for yn. And instead of n for yn minus 1, we'll just put n minus 1. N minus 1 by 1 by 4. Fine, this is. So this is what? This is lambda capital D by small d n minus 1 minus 1 by 4. What is the difference? See, this we have obtained already. This was n. Here you had n minus 1. So this is like n minus 1 by 4 only. Since here it is n minus 1, so we had to keep here as well n minus 1. Now, if you solve this, you take lambda capital D by small d common. You're left with n minus 1 by 4 from here. This becomes minus n. Then this becomes plus 1 by 4. 1 by 4 cancels and n gets cancelled. Only 1 is, that is beta is equal to lambda capital D by small d. I have told you earlier as well, for wherever you have fringe width, this will always be lambda capital D by small d. Last part said you have to find out the central fringe condition or something like this. No, it was given. Locate position of central fringe. C is for central fringe. N will directly become 0. Now yn is equal to n minus 1 by 4 lambda capital by small d. This becomes the condition of central bright fringe. Condition for central bright fringe. Now put n as 0, take the mod already. So you will get 4t like this. Why n0? Because that is the condition of central bright fringe. Like this, you will get questions. So this was a little tough question. You can get this as well. But questions are direct, simply formula based, the way we did the earlier questions. Note this down. Any difficulties, any queries you have, do let me know. Now we'll start with diffraction. So interference is completed. So that's why I'm asking. Any doubts if you have, let me know. All right, class. So let's start with diffraction then. Till here, interference, this entire topic is clear by all of you? Yes or no? Or any doubts you have?
Clear, ma'am.
Clear. Only clear to Krishna or everyone? Krishna and Hamza have only responded. Others, yes, Atif, Hanifa,
Clear, ma'am.
Sara, Kulsum, all of you others? Okay. Any doubts you have, please let me know. Now, see, next topic that we have is diffraction. This is the last topic of your wave optics. This is basically the bending of light. Now, how will the light bend? And light rays are coming. This is the screen. This is an opaque object. Now light rays are coming. The first light ray will come here. The second light ray will come here. Third light ray will come here. You'll obtain here the light. When the light ray will come here, this is an opaque object. It will not be able to move. When the light ray will come here, it is again an opaque object. It will again not be able to move. Here also it won't be able to move. Here also it won't be able to move. But as soon as it strikes the corner, no, the light rays bend a bit like this. Like this. The light rays bend a bit from the corner. So this phenomena of bending of light from the obstacle, you say, or any aperture, you say, or corner directly, you can say corners. This is known in the path of light. Whenever there is an obstacle, the light gets bent, and here, no, wherever the light is not present, you obtain geometrical shadow. Fine. Also, so this phenomena is known as diffraction. What is the phenomena of diffraction? It simply says that bending of light from any obstacle, you can say any aperture, you can say that is placed within this path of the light. Due to this object, the light rays bend. See, the light rays have bend like this. Bend light rays. They can penetrate into the geometrical shadow. And also remember this aperture that you're able to observe, no? This aperture, or the size, you can say, size of it, the aperture of it. It should be less than or comparable to the wavelength for diffraction to occur. I'll write down the point here. Size of aperture should be less than or comparable. If it is almost equal, then it's okay. Comparable to the wavelength. Then only diffraction can occur. Now, diffraction are of two types. One you have Fresnel diffraction, other one you have as Fraunhofer's diffraction. So these are the two types of diffraction that are present. So Fresnel diffractions, basically, when the separation of this is the screen, this is the screen, this is the source present, here is the slit that is there. This separation is finite. This separation is finite. You can calculate it. This is 5 meters. This is 4 meters. This is source. This is slit. You can calculate. That is known as Fresnel's diffraction. That is not a part of your syllabus, so no need to go into the details of it. Just remember the names. But if the separation between the source, the slit, the screen, all these are infinite, so then means the type of diffraction now that will be obtained, that is known as Fraunhofer's diffraction. So separation between the source, slit, and screen, everything is infinite. And here it is finite. This we have to study in detail, and questions come from Fraunhofer's diffraction. Also remember the wavefront that forms over here, no, in case of Fraunhofer's diffraction. Wavefront is a plane wavefront. I hope you all remember wavefront. We did in the first class Heinz principle. Locus of all particles, continuous locus of all particles that transfers energy, that wavefront only. So plane wavefront form is formed in Fraunhofer's one, because definitely source is placed infinitely separate at an infinite separation. Do one thing, note all these points, then we'll do single slit diffraction, that is Fraunhofer's diffraction in detail. Note down these points first. Yes, class. Now diffraction at a single slit diffraction, you can say Fraunhofer's diffraction as well. Fraunhofer's diffraction. Now see, this was an experiment done by Fraunhofer, so that's why certain things are already pre-decided. How will it occur? Now see, yes. A single slit is there. Single slit means like this. Double slit is not present. Once complete single slit we have. At this end, one lens has been taken. This is one lens. Fine. Now one more lens we'll have it. This is not done every time for every diffraction experiment. As I'm saying continuously, this was an experiment that was already done. Hamza, what about your experiment, investigatory project? Where have you reached? What did you decide? Let me know. So like this, sources have their rays of light. Now what will happen? These rays of light will reach this point. Same thing from here. Same thing for this also, you can write it like this. This is what? This is a complete opaque object that I have taken this. This part, no, that you see this. This is an opaque object. Okay. So Wheatstone bridge, you have taken it. Fine. So I think Wheatstone bridge. Just prepare for the viva of it. Many questions are like, if we change the jockey and the galvanometer stick opposite to each other, so what will be the difference? Like these questions come from Wheatstone bridge, the investigative project in viva questions that you have. Otherwise, normal displacement that is there to display, that is fine. Just this, if you interchange this, then what happens? If you increase the current, what will happen? If you change the rheostat value, then what will happen? Such questions will be there. So at the center of this, exactly at the center, you will obtain what? You will obtain a central maxima. Central bright fringe, the way we say, no, central bright fringe. Here in diffraction, we'll say this is central maxima. Now this is simple straight one. Now because of diffraction, what will happen? Because of diffraction, see at the corner, this light has bent like this. Similarly, at this corner also, this light has bent like this. Let's say from this corner as well, this light has bent like this. This is theta n, this is theta n. Now a perpendicular I am dropping. Let's say this point is C, this point is D. A perpendicular I am dropping, that is, this point is N. Fine, this perpendicular just I have drawn it from here like this. So here that you will obtain, this is the screen. Again, here you will obtain very few patterns. You will be able to observe the difference in the fringes that will be formed in diffraction and interference, that I'll tell you. There will be difference in case of the fringes pattern that will be formed right now in case of diffraction, and rest of the things that were formed in case of interference. So that we'll see later on. But right now, just forget interference. Just think that you have only diffraction present. So now how will it go? Cn is the perpendicular, right? CDN, this is just a triangle that has been formed. And here, let's say this is some point P. And from the central maxima, again, you have the separation Yn. Now, class, the derivation part. This derivation is simple, not very difficult. See, if you look at this triangle, CDN, this is also theta n. This angle is also theta n. So in this triangle CDN, which you are able to observe, this triangle CDN, let me write it. This is theta n, this is CDN. See, now this is theta, so sine theta will be what? Sine theta n. This will be dn, that is the perpendicular, by the hypotenuse, that is CD. So dn by CD. dn by CD. So from here, okay, one more thing. See class, this separation, no, that this is, I'm taking this as A, the width of the slit which we see. So CD will become what? CD will become A. So I'll get the value of dn as A sine theta n. This is the value of CDN that I'll obtain. Fine. Also, one more thing, if you look at this triangle, then tan theta n also you can write it as yn by capital D. Why yn by capital D? C class. Look at this triangle, this bigger triangle, this one. Here what is happening? Yn is the perpendicular, this separation is the base, and angle is theta. So from there you can write tan theta as yn by capital D. So even if you want, you can use small approximation and write is angular separation, yn is linear separation. Now coming to the condition for nth condition minima, secondary minima. We use the term minima for bright fringes and maxima for dark fringes, the way we had bright and dark fringes. Minima. So A sin theta n is equal to n lambda. Fine. From here n can run A and all. So see class, sin theta n will become what? N lambda or sin theta n. So this will be equal to n lambda by is a screen sharing with you? Just check class.
Yes, ma'am.
Yes. Okay. Let me know if you are unable to see the screen. All right. So theta n is equal to n lambda by A. So this is what? This is the angular separation. Now, what if we want to find out the linear separation? Theta n is the angular separation. See, yn was theta n into capital D, and theta n is this. So yn will be n lambda capital D by A. This is the linear separation. Now, linear and angular separation for what? For the minima. What about the maxima, where you get all the crests added and all the troughs added, where you get the maximum value, that is the maxima. So here the difference that will be arise, you will use the formula, the path difference formula for secondary maxima is 2n plus 1 lambda by 2. Now keep in the same derivation, same thing. A theta sine theta n is equal to 2n plus. So sine theta n will be equal to 2n plus 1 lambda by 2a. So equal to theta n, this be almost equal to 2n plus 1 lambda by 2a. This is angular tan into capital D. So yn becomes 2n plus 1 lambda by 2a just multiplied with capital fraction. All right, note down this. Okay, let's practice one numerical on this. So this says what a parallel beam of light of 600 nanometer falls on a narrow slit resulting in diffraction pattern. All right, so wavelength is 600 nanometer. Parallel beam of light of 600 nanometer, that is wavelength is 600 into 10 to the power minus 9 meters, falls on a narrow slit and resulting diffraction pattern is observed on screen 1.2 meters away. It means this is from 2 meters away. This is the separation between the slit and screen. That is 1.2 meters. It is observed that first minimum is at a distance of 3 millimeter from center of screen. From the center of screen means central maxima. So separation of the first minimum from central maxima is 3 millimeters. That is y1 is 3 millimeters, or you can write 3 into 10 to the power minus 3 Vt meters. And n is equal to 1. You have to find out slit width. A is missing. C class. Y is equal to, y1 will be, y is equal to what? N lambda capital D by small d. Small d, no, here I'm using the term A. Or let me directly write it. A, you have to find out. The rest of the things are given to you. Y1 will be equal to lambda capital D by A. So A will be equal to lambda capital D by Y1. So A is equal to 600 into 10 to the power minus 9. Capital D is 1.2 by 3 into 10 to the power minus 3. So this becomes 224. So 2.4. 2.4 into 10 to the power minus 4 meters. Let's do some more numericals as well. One numerical is not just sufficient. Note it down, then we'll do. Copy it. experiment, light of wavelength 6000 angstrom is used. Fine. Slit width is given to you 2 millimeters. Separation of slit from screen is given as 2 meters. So capital D, small d, lambda, all these are given. First, minima you have to calculate. That is n is 1, and the formula of minima. Just now that we have written angular and linear both. See, I'm writing down the solution. I'm discussing it with you. Wherever you're not able to understand, please stop me in between. For the first part, see. For the angular, just now we have written n lambda by a. So for n as 1, because this is first minima, theta 1 will become simply lambda by a. So theta will become lambda is 6000 into 10 to the power minus 10 meters. Slit width was what? Slit width was 2 millimeters, no? So 2 into 10 to the power minus 3. So that makes it 3 into 10 to the power minus 4 radian. This is just angular separation. We also have to find out linear separation. So same thing for C, linear separation. This is simply theta 1 into capital D. So 3 into 10 to the power minus 4. D was 2 meters, no? So 2, 6 into 10 to the power minus 4 meters. This is the first part. Second part says same thing. N is 2 and the formula will be used for maxima. It means theta n will be 2n plus 1 lambda by 2a, and in place of n we'll be using 2. So theta n will become 2 into 2 plus 1 lambda by 2a. That is 4 plus 1, 5 lambda by 2a. So theta n will become 5 into lambda is 6000 into 10 to the power minus 10 by 2 into, this was 2 into 10 to the power minus 3. So this becomes what? 2, 4, 7. 75, 7.5, right? 7.5 into 10 to the power minus 4 radian. Same thing, y2 will be what? Theta 2 multiplied by d. 7.5 into 10 to the power minus 4 into 2. That becomes 15 into 10 to the power minus 4 meters. This is how we will solve it. Simple, easy, just formula based. Understood this or not?
Yes, ma'am.
Okay, good then. Done, Sarah? Fine. One last numerical. Let's see. So all these parts you have written, all of you. If anyone wants to write it, let me know. This question says that a parallel beam of light of wavelength 600 nanometers. This is incident normally on a slit of width A. If the distance between slit and screen is 0.8 meters and distance of second order maximum from the center is 15 millimeters, it means 15 millimeters is what? This is the Y2's value, 15 millimeter. And second order n is 2 maximum. It means formula of y will now become what? 2n plus 1 lambda capital D by 2a. This will be the formula because maximum is there. Maxima. Lambda is given as 600 nanometers. Capital D is given as 0.8 meters. Yn is given as 15 millimeters. N is 2. A is unknown. So now I think it's a formula based question. We'll be able to calculate this. So see, class C, so many questions we have done. Questions like this only will come. So y2 will become again 2 into 2 plus 1 lambda by 2a. Now see, this becomes 5a. No, this becomes 5 capital lambda capital D by small 2a. 5 lambda by 2a. So from here, a will become what? So from here, a will become 5 lambda capital D by 2 by 2. So A will become 5 into wavelength was 600 nanometers. So 10 to the power minus 9. Capital D is 0.8 by 2 into Y2 is 15 millimeters. So 1 by 3, 6 gets cancelled. So 0.8 will be left. So this becomes 0.8 into 10 to the power minus 7 meters. Fine. This is the slit. Note down this question. Now, a very small topic that is there. We'll do this. This will be the last topic, then we'll wrap it up. See, the way we had angle that was subtended by the central bright fringe, no. Here we'll have from the first minima, the angle that will be subtended by the central maxima. We are calculating. So let's say if this is theta 1, this is theta 2. So angular with entire angle will become what? 2 times theta 1, because obviously this angle is same. So it means angle and theta was already lambda by a. So this becomes 2 lambda by a. So linear width is what? Linear width of central maxima is basically angular width multiplied by the separation. So it means linear width is equal to 2 lambda capital D by A. This is the formula. This is the linear width, this is the angular width. So basically width of central maxima is this. I'll stop here today. Very small topic, that is intensity distribution curve. We have very small things that are left from wave optics. Wave optics is almost completed. Diffraction is also almost completed. Half an hour, I think, will be taken on Thursday to complete this. On Thursday, I'll not take the test of entire wave optics. I had announced the test that I'll take a test of wave optics this week. So I'll not take the entire test because diffraction has been completed today only. So how will you be able to revise it? So only interference I'll take the test of only interference. Heinz principle plus diffraction, I'll take it later on. Only interference test, I'll take it on Thursday. So as soon as you all will complete, you all can text me done and can leave.